Thank you for joining us for our second Agronomy seminar this semester. Today, I'm pleased to introduce Dr. David Rossiter from Cornell University. Dr. Rossiter is an expert in soil geography, spatial environment modeling, with a special focus on digital soil mapping and geostatistics. Also using R programming to do most of his work. Over the years, he's worked in a wide range of international settings. He spent 17 years at the University of Twente in the Netherlands and continues to collaborate with the ISRT World Soil Information. He's also been active in China, working with the Chinese Academy of Sciences and Nanjing Normal University, and worked on soil hydrology in India. Dr. Rossiter brings a global perspective and practical approach to understanding soils and landscapes. Please join me in welcoming Dr. David Rossiter.
Okay, can you hear me all right? Okay. Well, it's a real pleasure to be here in the heartland. My mom was from the Midwest. She was from Milwaukee, and she always told us the Midwesterners were like the best people. But I grew up in the degenerate Northeast, so that was it. So my affiliation, I'm an adjunct at Cornell because I've been retired from my university in the Netherlands for about over 10 years now. But so adjunct means they don't pay me any money. I give them advice, and if they take my advice, it's what they paid for it. So, and ISRIC, you might not know, is in the Netherlands. It's the international organization that is for the standards of soil data and collecting soil data from all over the world. So after I retired in the Netherlands, I stayed there. So I'm a dual citizen of the two countries. When I went to be a citizen of the Netherlands, they asked me, what happens if we have a war between the United States and Netherlands? Which side are you going to pick? I said, I'm going to get under the table and hide. He said, that was a good answer. Okay, these are the questions I'm going to try to answer today. I know I have a mixed group. Some of you are very, very experienced in digital soil mapping. Others don't know anything about it. But what I really want to focus on is the fourth point here. Well, the expenses, of course, what can it do for you? But where are our problems? Because I think there's been a lot of overselling. There's good and there's not so good. And I want you as consumers to have a fairly clear idea of what it is, what it can do for you, and what it really can't. I should say from the start, being here in Iowa, you really don't need this because you have fantastic soil resource information already for you from conventional soil survey and then digital work. So this is maybe more relevant for those of you who are going to go outside of the very, very data-rich environment here. So let's start with conventional soil maps. I think a lot of you know this, but I just wanted to show the difference. What we can see here is a map of polygons. And each polygon, inside it is supposed to be one type of soil or more or less homogeneous type of soil. This is a beautiful map that was done as part of a transporter project where the Dutch and the Germans each mapped a transporter area, and they both published maps. And I only have the Dutch map here, part of the Dutch map, and they're different. It's kind of interesting because the two conventional maps with different concepts of conventional mapping look different. The major ideas are really clear. I also like this map because of the very nice link to geomorphology. What you can see here is how the soils are following geomorphology, and in some cases, for example, down here, these little red dots are from artificially raised fields, so they're anthropogenic influence. But the map almost shows you a picture as you see it, right? A conventional map. Here we have what we have in the United States. You have this in Iowa, conventional map where we've got these areas that are delineated out. These have been digitized, and you can, so the same information that was done on air photos will now be, but it's not a digital soil map. It's digitized, so it can be used in the GIS. But you still have these polygons that inside you describe one thing. And for example, here, this little dot here is a particular point. And in this unit, we have this idea of a representative profile. And from that, we can get all these information about it. So, but we don't have a map point by point. We have a map in polygons. And when we want to say we go to a given point, we take what's in the polygon, we find the map unit legend, we go to the database, we find a representative profile, we find the lab information, and we apply that to that whole area. There are sometimes estimates of different soils that are in there, but those are we don't know where they are. So they may say, well, they're 10% of a different soil, but you wouldn't know where it is. Okay, so that's the concept of the conventional soil mapping. So what they're made, and this is a big contrast to digital soil mapping, the idea is experts judge the soil forming environment, and based on that, they stratify the land into areas where the soils will be similar enough within those areas, based on these external clues. So typically, you're looking for the landform, the land use, vegetation, information from air photos, and then you go out there make some purposeful soil information observations to check your work. But essentially, you look at a tiny, tiny, tiny part of the soil. But based on your expert knowledge and your idea about soil formation, you can end up making this map. You then, of course, take it to the laboratory to characterize this, make a map of the report. So one of the main things to notice here is the reliance on expertise, right? So why digital soil maps? So conventional soil survey is quite expensive and slow. And a country like the United States with a lot of resources and put a lot of into the years over it, the cost of the soil survey program, I don't even want to know how much it was over the many, many years of people working. So it's fine, it's expensive, slow, but it also requires a lot of expertise. In my first part of my career, when I graduated, I worked in North Carolina as a soil surveyor. And I can tell you that some people, when you're doing your soil survey, you have an air photo, and you're out on the land, and you made your lines where you think things are going to be. You go out and you check them, check the boundaries. You're walking across the landscape, and when you come to the edge of your air photo, you come maybe to another guy's mapping. So your mapping is coming next to the other person who was in the field part. And sometimes as you're coming close, and you have the previous map there, so you can see you'd like your line to line up with his or her line. And when you get closer, sometimes you're thinking, yeah, this makes sense. This makes sense. I like this. I like this. And then when you get there, oh, I see what you saw, and everything's fine. But there are some times I come to a border of a map. I say, what was this guy looking at? I can't figure out. Sometimes I can say, oh, I come from this. I see what he was looking at. I disagree. But sometimes you really wonder. And these maps are still there. So the problem is the expertise can be varying in quality. That's one thing I want to say. You draw the polygon subjectively, and you have these very crisp boundaries. You have to make a boundary, even though we know they're transition zones. And we have no estimate of uncertainty, only very vague ideas of uncertainty. So if I want to go to a spot, and the map tells me it's this, with this much organic matter or this thickness of the solum, how certain is that? We really have very idea. And finally, the impossible areas. That's not really the case in US because the law allows you to go everywhere, but other countries, it can be difficult. You go to war areas you can't get to, you can't even go into. They can be very difficult, or it can be areas that you're just not even allowed into, right? But what are the needs we have beyond conventional soil survey? Land surface modeling has been the real driver for this. So hydrology models like watershed models, emissions, sequestrations, stocks and storage, soil fertility, that a lot of these models want to have information everywhere, and they want it on a grid basis because these models work on a grid basis. So you'll have the watershed divided into grid cells, and the hydrologists will follow the water coming into the soil, traveling through the soil, etc. So there's this big demand for this. And already back in 1986, Zobler generated a 1 degree, which is about 111 kilometers, general soil class that they were using for the early climate models. So what they did is they took the paper map of the soil map of the world, made it 1 to 5 million by the FAO and UNESCO, just put the grid on top of it of 1 degree and picked out the dominant soil in there and the average texture. But it was much better than nothing because these modelers needed to have something that tells them how much water is being stored, how much evaporation. So already they were doing that. But now the model requirements may go at all these resolutions right down to 10 meters. Another one I mentioned here is the objective and reproducible. So I mentioned that the Germans and the Dutch, they both looked at the same area and the maps look different. Well, neither is right or wrong, but you'd like to be able to reproduce, okay? You'd like to quantify the uncertainty, and then finally the updating. If you get new data, new information, can we update and improve the map? Either it changed over time or we just have better data. So these were the needs of conventional soil survey. You can't really update a map very easily. You can go to specific spots if things have changed. Like we had some years ago in upstate New York, we had a really big hurricane that completely reworked all the soils in the floodplains. You could go back there and remap those because the texture completely changed. But that was just one spot. You couldn't do it everywhere. Okay. So digital soil mapping also is linked a lot with the overall development of the digital world. So already in 1970s, when computers became accessible, at this point they were mainframes. And if you don't know this word, it was a coined word, repetometricians, metric from measuring and pedo from pedology. So a colleague of ours, Alex Bradley, he likes to coin terms. But anyway, geostatistics were developed. And one of the first papers with Mike Thompson and Harold Van Ness, right, was on geostatistics here so many years ago. But then we got very interested in the landforms. The digital elevation models now became, especially when the Hubble radar went over, digital elevation, and you can now characterize the landform. Statistically, you can measure the local relief, the slope, the catchment, etc. So those are obviously very related to soil. So already the 1990s that got started. Then I'm saying 2001, but this was a movement before this came up, this idea of statistical learning. Some people call it machine learning, which I don't like the word. It's really statistical learning. Many techniques became available, and we all started reading those techniques, and we realized these techniques could well be applied also to soil mapping. And then in 2003 became this model I'll talk about in a bit, this formal definition of digital soil mapping. Then came an initiative to make a global soil map, which a project that has ended up in some standards, but not the global map. But it was an idea of methods and standardized methods and so forth. And then finally in 2014, Tom Hengel, who was my PhD student in the university in the Netherlands, who then went on to work at ISRIC, he and his group published the first soil grids. And recently in 2020, we published the second one. And by the 2020s, this has become totally routine. I will say, what I mean is many groups can do it. So this is first evolution. So what are we trying to do? We want to predict soil properties, sometimes soil classes, at all cells over a fine grid. So over some area at some resolution, we want to make a prediction everywhere. What we do is based on some training observations. Obviously, if we haven't looked at the soil, we can't do anything. So we look at the soil, we know at certain points what there are. We looked at that, we have it. And there are two methods based there. For small areas, geostatistical interpolation such as creek. So if you have lots of points, you can just attempt to interpolate those using something like kriging over your full grid. But at larger areas, that's impossible. So there are these statistical learning methods that attempt to take the points we do know and all the environmental factors at that point, build some statistical model that relates those. And then once we build that model, we can apply it everywhere else. That's the concept. The nice thing about this is intrinsic to the modeling methods, both the kriging method and also the machine learning methods, is you automatically get an estimate of prediction uncertainty. So already and I'll show you some examples. So this is how digital soil mapping, this is what it is. The name is maybe not so good, what is digital, but anyway. Okay, here's the first to show you the difference from the most recent product in the United States. On the left is the depth of bedrock in an area, I think, will border between New Mexico and Colorado, and on the right you see the conventional map. And I think you can obviously see the problem that the two states had different concepts, different soil series, and when those are translated into the depth to the bedrock or restricting area, you see the obvious state line, right? The map on the left, on the other hand, is made from all the training points that were available anywhere, and then predicting everywhere, and it doesn't know anything about states. It could, by the way, you could put the state in as one of your covariates, but that doesn't make much sense in soils, right? How is what state you're in affect the soil? Well, maybe there were different regulations in different states. It could. Anyway, so this is an example of comparing it. This is the statistical learning. This is the Bible of the statistical learning book. If you don't know this book and you're into statistical learning, I highly recommend it. There's also an online course taught at UCLA of a simpler version of this. It's a free online course. But the basic idea is we have these georeference training points. So we have to know where they are, and we've measured the soil properties in the lab, or we've named the soil class that we know there at that point. Then we overlay this with what I call full field covariates, which are something we know over the whole area. For example, a climate surface or an elevation model, terrain derivatives, land use, satellite imagery, something we know everywhere. But then at that point, you put a big pin through it and you know all those things at that point. You build a statistical learning here, which is this, and there are many methods of statistical learning, but they're all relating the what you know at these points with these covariates. You then can evaluate the model quality. There are various ways to do that, and then you predict over the grid cells. This is how statistical learning works. So the conceptual basis is based on this concept called homosoil, meaning that if the soil forming factors are the same, the soil should be the same. This goes all the way back to Jenny and even all the way back to Dukachayev. The idea that these are the main, why is a soil where it is? Well, the climate, organism, relief, parent material, age, and recently has been added the neighborhood, something about the spatial neighborhood. So the concept is if we can find layers that represent these, then if we can make this model, correlate this model, then we'll know what soil it will be. I should say that this is a bit difficult because there are many ways to characterize these things. Just to give you an idea, in the soil grids product, which I'll show later, which is the entire world at 250 meter resolution, we use 400 plus covariates, and it's hard to read, but it's divided weather and climate, ecology, geology, land use, elevation, morphology, satellite, vegetation indices, hydrography. So these are the kind of covariates. So these big statistical models are relying on over 400 covariates. And this is why this computer power has made this all possible. This is the workflow, soil observations and covariates. You overlay them, you make this matrix. There's some optimization going on over here. All the different methods can be refined by certain types of optimization. That's pretty standard now. But then you fit the model, and you make a prediction model, and then you can make your maps, and you have a map of the prediction and of the uncertainties. This is a much smaller example that I just took out of a very recent paper from fertility mapping in Morocco. And I picked it out because it's a typical example of what people are now doing all over the world. This is just a group from various ministries in Morocco. They did it for phosphorus and potassium. They had large numbers of field samples. Yeah, but my office mate at Cornell is Moroccan. He's a PhD, he's a postdoc. And he told me, oh yeah, like the 30,000 points that another group won't give them. So this is a big problem around the world. These guys could use like 5,000 points, and he says, oh, there are 30,000 points in another project that's been published. They won't give it to anybody. So Anyway, but you see they make the matrix, they make the selection, so it's the same thing. So here's some example digital soil maps. This is our soil grids product. And I know we have Argentinians here, so that's why I picked this example specifically. No, it's just by coincidence. And what you can see here is that we have these standard depth slices. So we have these 7 depth slices, and with our properties, both physical and chemical properties. This, I happen to have the pH here at 15 to 30 centimeters, and you can see these big differences. So when you zoom in, however, you see something like this. This is from the same product, but it's something completely different. This is the sand of the 0 to 5%, to 5 centimeter layer, but in the grams per kilogram of an area in Pennsylvania. And when you look over at the big map, if you know anything about the Ridge and Valley province in Pennsylvania, it looks really good. The red areas are these limestone areas with very, very little sand. They're residual from limestone, ultisols with limestone. The bright green areas are these high sands, coarse sands that are on the resistant sandstone ridges. And at the north of the Allegheny Plateau. So everything looks pretty good there, but you can see that it's pixel by pixel. And on the right, you see an example of just a small area where it really doesn't make any sense. You see differences that probably aren't there. There's no real reason to think you have so much difference. So the map is predicting at each location, but it may not predict so correctly at each location. This is another example of a project we did, a paper I did with my colleagues in Nanjing at the Academy of Sciences on soil colors. So we had about 4,600 points where soil colors had been recorded. And so we made maps of all these depths of the soil color. And these were, so now we're predicting in different color spaces. And it came out really, really well. But the interesting thing I want to point out here is there's an average of 2,100 square kilometers per observation. So only 4,600 points for all of China, which is a big area, right? It means that if we have a good model that the covariates well represent the feature space, the predictor space, we can make a good map even with not very many points if we well represented. And the reason it worked in this case was this project to design the soil series in China, in Chinese soil taxonomy. They specifically went to look for representative locations. So you had really good representative points. So the colors would be very representative of the landscape elements that were there. So that's one example. Here's a Morocco map just to show you. They only predicted in the agricultural area. So the uncertainty, I mentioned the uncertainty. So what's going on with the uncertainty? How well you reproduce the known points you can do by splitting the data set, cross-validation. But the problem with that, with all of these, is they're not based on a probability sample. So when you look to say, well, how closely could my model predict back at the points I know, since those points were always selected by not to be statistically independent, they were for some other reason, some other survey, you can't really have a lot of confidence in these numbers. These are reported in many of the papers, but they only really tell you how well the model did based on these points that you have. And it's very difficult to say something about areas you didn't know. And you can see how bad this is with soil grids. Now I picked a location, this is the soil grids product, and I've zoomed in, and you can see the pixels there. These are 250 meter pixels, and the place in Van Meter, Iowa. And why did I pick Van Meter, Iowa? Bob Feller. Thank you. My father served with Bob Feller on the USS Alabama in the Second World War. And then if you don't know who Bob Feller, one of the greatest pitchers of all time, and my father tells me when they would play baseball, when they get to some South Pacific island and they could relax, they would play baseball, the teams against the different ships. And Bob Feller could play, but he couldn't pitch. They let him hit, and he hits like 600. They let him hit, but they wouldn't let him pitch for obvious reasons. Anyway, So that's why I picked. When I was a boy, for some reason, then I read his biography because my father had been in the Navy with him, and so I picked Van Meter, Iowa. But anyway, thank you. I'm glad I knew someone would know this. Are you from there, or you just know that?
Actually, I have a glove that's signed by him.
Okay. Bullet Bob.
Yeah, grew up in Des Moines and he came to an Iowa Cubs game.
Oh, all right. Oh, the Iowa Cubs. That's right. You were the Iowa Cubs. Anyway, let's get back to the subject. And if you look on the left there, oh, come on. Culture is important, right? So on the left, what you see is the uncertainty. So let's look at the pH here down here. So it's between 6.5 and 7.1 through this profile. But if you look at the gray band here, this is the 5 to 95% confidence interval. We're using random forest here, which made many trees in the forest, and you take the trees and essentially say, well, leave out the lowest 5% and the highest 5%. What's the range of these trees? And the trees got a way to be different. So you can see the uncertainty is fairly high here. We actually go down, we actually go down from about 5 to about 8, even the surface slope. And of course, that's impossible, right? We can't have a soil that could be 5 or 8. I mean, but it's really bad it's really bad for cation exchange capacity. And look how carbon, so this is an honest model. You could use this in modeling, by the way, because you could say, well, I can assume a statistical distribution here and I could use it for sensitivity analysis. We don't think the predictions are particularly bad, but we do think that the uncertainty is a fair idea. Now, this is a model based on all the data from the entire world, not specific to Iowa. And if you would have a more local model, it would probably be better. But this is how that works. Here's an example from upstate New York, and this is all pH. On this side, you have the 5%, the median, and the 95%, and you see these areas go from pH 4 to pH 8. The middle map actually looks pretty good, if you would know that area, but the uncertainty is quite high. So one thing I want to emphasize that when you use digital soil mapping, it's giving you these uncertainties. Another problem is the temporal changes. Some people are thinking about using this for carbon accounting, where they're going to try to say carbon has changed over a certain amount of time. But when you look at the uncertainty of map A and map B, and then the uncertainty of the overlay, you really, really wonder, is it even at all possible to detect even a real difference by this method? You can do it point by point, of course. You can go back and revisit a point and you can find out has it changed. But if you're taking a larger area and you want to know, has the carbon really changed? So that's something we would like to do. So what are our successes? Many projects, maps are widely used, and the number, it scares us. I get citation alerts for papers that I'm an author on, and I'm one of the authors on the second one, the newer paper. And every day I get 5 or 6 new references to soil grids. And the uses they put to them, I am amazed, and I'm just upset, really. You know, they'd be, mollusk diversity in Africa or something using our, and you say, okay, because people will say, I need soil information. They're being a bit lazy, right? In the sense, not everyone, but saying, I need soil information, there it is, I'm going to use it. And it's even used by sometimes modelers in countries with good data. They'll still use this. So look at the number of citations there on the 2 versions of it. Also, but the other thing is in the United States, Netherlands, China, in sub-Saharan Africa, EU, there are big projects using this to make wide area maps. One nice thing about it is it avoids country boundaries. So it's been very, very good that way, that when you had different soil survey organizations with different standards, rather than stitch together the maps, if you just take all the points from the different organizations, as long as you harmonize their lab methods. So the Hungarians use a different type measure of clay than the Germans do. So you have to make some transfer functions, but once you do some harmonization, and we're specialized in that at ISRIC actually, trying to harmonize these, then you'll get a map that doesn't the only national boundaries we'll see will the ones that have a real land use difference. Like United States and Mexico, if you look at the border at the Rio Grande, yeah, okay. The Colorado River, you're going to see that because there's a real difference by the countries because of that. But otherwise, you won't see the country boundaries. And the last point is this is getting really used all over the world. It's getting more and more accessible, so that's good. So those successes, advances, sophisticated learning. This is many papers on these. Although my idea on this is the method doesn't make as much difference as the data. Better points and better covariates are much more effective than your latest optimization of one of these models. You'll get these papers that say, oh, gradient boosting is better than random forest, by 2%. You say, well, so what? I mean, that's okay. I like having an optimal model, but that's not the main point. We have more and more training points. Now, there's a movement to more open and documented points, but there's a big problem getting training points from a lot of organizations for a variety of reasons. I'll mention those later. A lot of more covariates, more imagery. Satellite imagery is just going crazy. Every day there's a new satellite that can be used. I never thought we'd be using the night lights, but actually the night lights are good indications of heat island effects and urban influence on soil. So anyway, and we have some automated workflows. We have some other ways to assess uncertainty. That's our current, this business here that I mentioned with the uncertainty, the quad map and the area of applicability is my colleague, Laura Poggio. That's her main activity right now with our soil grids, is trying to show you exactly the effective pixel size that really can be supported by the data. So there's a lot of advances. We know what we're doing here, right? Another nice advantage, which is not only for soil mapping, but all machine learning or all statistical learning, is this idea of the interpretable machine learning is becoming more and more possible to see why the model makes a specific prediction. And you can then try to understand why that prediction is there. If it's not a good prediction, to try to understand why. Now we're also dynamic. This is something we've done at Cornell. One of the students I was on our committee, Valentina Rubio from Argentina, working at the national organization there now. The idea is, can you map some of these more dynamic properties? And the NRCS has also got a whole group on dynamic soil properties now, not only carbon, but also things like compaction, erosion, and so forth. So what she did is use the cropland data layer that's been going on since 2010 to say these are the management systems, right, and include these in our models. And so the management system of it, the land use system of the cropland data layer is only approximate the real management options, but at least it's something. I mean, we have in upstate New York, we have a big Amish community that works very differently than Anglo farmers. And so that's not captured by this, but it's a big influence on the soil properties. Anyway, so you get these predictors of the dynamic soil properties. So this is an idea of how important the variables are, but the one at the bottom, you see the prediction system here. So these variables above the production system actually turn to be quite important in the digital mapping of soil health indicators. And then we did something very interesting, was to say, in a scenario analysis, what would happen to soil health if a land use system were changed? If we replaced an annual small grain system with an integrated system with hay pasture grains, right? So a rotation. What would be the effect of soil health? Because you now included it in the model. Since it's one of the predictors in the model, you can then apply it to another area and have a bit of a scenario analysis. And this is showing how converting in this one area, in these areas, would have on in the overall soil health index. She did a bunch of these indices, but this is an overall. But this is nice. You can do something with a temporal change. So what are the problems? This is what I really want to talk about. I want to emphasize for you. First off, with the bad predictions, right? Just bad predictions. This is even back at the points. And this is Solus is the most recent product from the NRCS, the entire country at 100 meters with these standard depths and standard parameters. Very similar to soil grids in the approach. And if you look, for example, here at the cross-validation of the pH, and I should say the pH is usually one of the best, easiest to predict, right? So if you look at the pH here on the left, and the darker the color, the harder the count. So there's a lot of points that are pretty well predicted between the measured and the cross-validated. But look at the big spread. There's still about 15 or 20% that are really, really badly predicted off by. I mean, they're saying that down here you're measuring a pH of about 7, and the map says it's about 4. So it made the extremes, and some of these are really bad. If you look over on the far right, this is the restriction depth. Very important property. What's the depth to a root restricting layer? And you can see it's just a total mess. So I mean, I'm not being I'm not trying to be critical. I'm saying with the data available and with the models available, you can get sometimes this bad predictions, right? So that's the first problem we have. Second, I mentioned already, I showed you the wide prediction intervals. The model says this is how wide it is, and we really feel that it's unphysical. Often you can even say it's unphysical. You can say that range is impossible to have that range. pH is a good example. I mean, there's no way I'm going from 5 to 8, right? I go to 5 to 7.2 or something. I mean, there's no way it could be that bad. And this is an example from Solus. And if you look at the upper left, here's the mean prediction compared to the conventional. So here, number B is the conventional one. And you could focus on the sandhills here in Nebraska. This is the prediction of this is the clay, right? Clay. So very little clay in the sandhills in Nebraska. We know that, right? Solus does pretty well with that. You can see that. But look at the and it does quite well. It has the interval's not very wide either. You see the sandhills in both the low and the high, so it's got a low interval there. It's probably very easy to predict, so the model is there. But if you look at some of these other areas, look at the Mississippi River. Look at the delta here in Mississippi and Arkansas. The link between almost no clay to like 90% clay. Now the mean prediction here doesn't look too bad at all, right? These are the soils, the Mississippi Delta soils, the rice soils. So this is just to show you that the prediction intervals are often quite wide. But when we use a model, we should trust. When the model gives us both things, we shouldn't just take the prediction. We should also take the. So another problem is different models and different resources will give different maps. And I have a paper on this a couple of years ago. And the model's extremes. Let's look at this. Here's a nice example from an area near Montreal, and this is using convolutional neural networks just with 4 different window sizes, which is something you can do in these neural networks. And you can see the different predictions and the different patterns, but the cross-validation, R-squared and RMSE are almost identical. So there's nothing to choose between these maps based on the statistics. Obviously really different maps. What do you do? Which map do I show? Because his paper, he was trying to, I can't get him to publish this. He says, oh, I can't publish this. No, he says too depressing. Another big problem is we have that you wouldn't have in the United States where there's data everywhere. We have it a lot internationally, is extrapolating into areas where we build a model in one area and we extrapolate into an area where we have the covariates, but we don't have any points. And the theory is, if the situation is the same, we should get the same soil. So I have all this data from one country, an intensive study in Rwanda is a good example. A lot of data from Rwanda. So you build this model in Rwanda, and you just go right across the border to Uganda or Eastern Congo, and you say it's in a similar area, and it should be okay. But you don't really know, right? You hope the relation is the same, and you hope it's going to be good, but we don't really know if there's a local situation that will make that not true. So you'll see these maps of the whole world, and some of those areas are well calibrated and others aren't. So that's another problem. We use grid cell prediction, but that's when you do a hydrology model, you need the relation between cells, and we don't have any way to do that yet. And this is one I really want to emphasize. The resolutions that are being used, the grid size, can that be supported? In soil grids with 250 meter resolution, you can see the 1500 CPU hours, which is a lot, but it can be done on a high performance computer. 2 terabytes of storage. Again, it's expensive, but we can do it. So we can map the whole world at this. We could probably go down to 30 meters, right? Because we can get covariates, these sentinel, look at these. We can get planet satellites, maybe not the whole world. But the point being that the covariates are finer and finer resolution. People want to make the maps at finer and finer resolution. But can that really be supported? So what is the support of a training observation? It's about 1 meter, right? I mean, you know, I mean, maybe not exactly, maybe if you're bulking cores, maybe it's a little bit bigger, but theoretically, we could predict down to 1 meter and it would be supported by the data, but we don't have that data. And here's an example from in southern Kenya. And you can see on the left the 250 meter map, then a 30 meter map, and on the right is the air photo satellite imagery. And you can see the much more detail at 30 meters. But if you look at the points, look at the little white dots there, those are the only points that are really known there. And you see all this fine detail, but you really wonder, like if you look here and you see this very fine pattern, is this a realistic pattern? Are we picking up real differences there, or are we just having artifacts? And I showed you the example from Pennsylvania, where clearly that finer resolution, at that resolution, was picking up artifacts, for sure. So how to judge this is unclear. And the guy who makes these maps, Tom Hengel, he's making them finer and finer, but we're scared to do that. So problems of data sources is, I mentioned the low sample density, large areas with few observations. Sometimes we use pseudo observations, so we think we guess what the soil might be, like we did this with the Arctic soils, for example. Very, very few observations, but you get some ideas. I mentioned the closed data sets. Some of the culprits for closed data sets are surprising. France is a good example. France has a very strict privacy law. We can get 80 points from France that are only from like public research stations. And the paper was published some time ago where they could use their own 3,000 points or something, and they said, oh, our product are much better than your product. Yeah, well, okay. But they won't give it to us under any circumstance. So it's a problem. And then there's this wild west of databases that's going around I'll give you this, you give me that. What's the quality control? No one really knows. So. And finally, the poor reference of georeference. A lot of these observations were made before GPS. So they may be in the wrong landscape position. I came across a case of this in Uganda once where they're clearly in the wrong place. And when I consulted with the person who helped make the survey, we went back to the right place with the GPS. And now we had them in a good place that really did fit the model. So that's the problem. A lot of our data is older data. This is our training points for soil grids, and you can see all of Asia only has 7,600 points, right? Because of the data problem. India is a terrible miss. China. So if you look at Australia, by the time this is 43,000 points. So it's very, and of course the US is the champion, or North America is the champion. And then you see an area in South America where Bolivia has almost no points, and you see this Western Brazil, for some reason in Acre State or Rondônia in Brazil, which is on the right, there was for some reason some high density of observations. Embrapa, which is the Brazilian national agency, is very open, very collaborative with everybody. So we got their data, they're really good. But I think in Bolivia, there just weren't that many points taken. So then what do you do? So this is one of the problems. So yeah, I think I'll skip this one and go to, I don't want to bore you guys too much. This one is a very fun one. Our models are correlative. right? They're not based on theory. What we do is we pick covariates that we think represent soil forming factors. We put them in the big stack. What we did here is a paper where they artificially made Pangea, the old continent. They put a European soil map of soil organic matter on top of Pangea, right? So it's a completely hypothetical place. They then took the faces of 30 of us. I was included, but I did not get selected as a covariate. I got eliminated in the feature elimination. I don't know why. Maybe my face doesn't predict it. But anyway, we got a map with, and this is soil organic matter, RMSE of about 2%, and look at the mean error. I mean, and good statistics. And you see the pictures of some of the people you might recognize their name if you're in this field. And these were the top top 8 predictors that they were able to predict the carbon by using people's faces. So, and the question is, are we doing some of this when we're picking, all these satellite imagery? Are we seeing something that's really related to the soil? And this is another. So the unclear relation between covariates and soil forming factors. People are using remote sensing products. Some might be directly related, like albedo. Okay, that's fine. Others might be more indirectly related, like thermal capacity, but like day-night thermal differences related to the water content and clay content in the soil. Some might be related, and some are they just no obvious relation. And this is from the Moroccans, and why. I wonder why, climate minimum, temperature cold month, temperature rough scale, climate year precipitation. Why is MODIS EBI in March come out? Why are these things? Disappointments, I mentioned these. I'll go back to this. I talked about this already, so it's just a little bit of a summary there. One I didn't mention there, this is fourth one. The fifth one is products from wide scale maps like global map often performs poorly at local scale, even though the theory should be able to work all right. Now, what about the producers? And this is a part of a problem. It becomes so easy now to make these maps that there are people that are going and making maps or papers with like 15 points, and then you can do it. It'll come out, but it really can't be supported, right? People will use these methods, these very sophisticated methods, and they don't check the reality. A lot of emphasis on methods, and it's very easy to make map and get a paper, right? People are interested in getting papers, and they're not really thinking of they're not using it as an adjunct to understanding the soilscape. There's a lot of people who don't know anything about soils are getting into this business and making these maps. And statistically, it's a true statement, but then they don't really know what it means. So this is something that the producers. Then in the communication, I think there's a lot of overselling of products. I mentioned the overuse of soil grids. In other words, that's not. Is it that we're not communicating that you shouldn't use them beyond what they are? We have warnings, but you see people using these, taking them as reality. They don't understand uncertainty, and there's often another problem I have is there's often poor coordination with the local experts. So there's a little bit of what they call the helicopter research. You know what helicopter research is? You come in from outside. They use it for the geneticists who coming outside, take the plants, and they go away. That kind of thing, without working with any of the local. In this case, you often have local experts, but they're not involved. But we're very big at ISTRIC in this. We have a whole project of Africa Soil Information Systems. We have a community of practice. We're working with all the national organizations we can. So the idea is, we're making product for Africa. We're going to do it with the Africans as best we can, train them. And but there's a lot of that. That's a disappointment. So last point, best practice for you all. So if you get to, why use a digital soil map? First off, what's your target area of interest? Where are you going to work? Which properties are you interested in? What depths or what classes? So what are you looking for? So you look for a product that's going to give you the things you're looking for. How much precision do you need for your purpose, right? If you're just doing a case where you're deciding it's an extension job at some country where either no fertilizer, 1 bag of fertilizer, or 2 bags of fertilizer, based on a fairly general fertility recommendation, you don't really need a very precise map. That's okay. If you're doing something that's going to be modeling nitrate flow to a stream for regulatory purposes with strict limits, then you're going to want quite accurate. Your hydrologic properties you're going to want quite accurate. What uncertainty will you need? What resolution do you need? And do you need connectivity? Make sure you review the point accuracy statistics, even though I said they're not representative points, still that gives you some idea of how well they predict back to what they were doing. Are there areas where the uncertainty is too high for your application? Then you have to tell your user, I can't tell you. They don't like to hear this when you say, I can't. You ask me for information and I can't give it to you. I don't know enough. And one thing you can do with the land surface models is you can do the stochastic simulation and see if your results. So you take the uncertain data from the soil, you run it through your models, and you see how different is the outcome of your model. If that's not too bad, then it's good enough for your purpose. If it causes big deviations in your model, then it's not good enough. Look at the output. In areas which you're familiar, are the results realistic? Look at the big features, look at the small features, get some idea of what you're looking at. And I decided to, I gave an example from Iowa, actually, for this talk. And this is from your excellent lab. And this is a pH of the 20-50 centimeter layer compiled from various sources. You see the really, really clear, you wouldn't have this everywhere in the world. But so let's imagine, even though you don't have this, you have some idea of this. And here you very, very clearly see the different hills and different, you see the Lust Belt, you see the Des Moines Till, you see landscape features you really know. Although, look up here, see the problem with conventional mapping, right? There's a bit of a problem there. But anyway, if you look at soil grids, this is Iowa in soil grids, and I wonder, do we even recognize anything? Well, we sort of see southeast Iowa here, right? Here is the Lust area we sort of see, and we sort of see the Des Moines lobe. This is the same. This should look like this. Not exactly, only showing kind of the middle part of Iowa. So you would look at this and you would say this product on a synoptic view is missing the major features that we need, that we would need in for our purposes in Iowa. So you would reject this, right? So this is one way to do it. And I have a couple of examples from my experience in North Carolina, which I think I'll skip by. So the last slide is, I think, a nice example from a paper that they looked at the digital soil mapper at these various resolutions, failed to meet accuracy requirements for site-specific farm management. So these people said, well, we can't use this for even farm level planning. But in this paper, they said additional data would be required. But we see this resource as a low-cost alternative to lab-based soil tests. It has value in reducing uncertainty around soil properties compared to having no information. And I think this is one way to think about it. Don't take it for truth, but take it as reducing your uncertainty, and almost like a prior, it gives you some idea of what you might find when you get there. The better than nothing. But don't be fooled by that map that shows you all this fine detail. So that is my presentation. Sorry it went on a little too long, but hope it was entertaining. I have many more stories I could tell. Especially when you're an old person, you have a lot of stories. Heidi had to listen to me for an hour coming back to the airport. She knows all about it.
It was great. We have time for 1 or 2 questions before we go.
David, I'd like to ask about soil grid. Can you give us a couple of examples where soil grid has been applied at an appropriate scale to the 250-meter grid.
You mean papers where it's been applied?
Any kind of application where it's been useful, where soil grid has been matched appropriately with the scale of the data to make a useful prediction for somebody.
I have to really.
250 seems pretty large to me. And I just wonder what are the
It's being used a lot.
at that
It's being
scale?
used a lot in land surface in India for the emissions people. But I must say, with all those thousands of papers, I haven't looked into detail how they're using it. You're really provoking me to do this. And I'll. Yeah, and my boss, I mean, the head of the ISRIC, who's very interested in let me think about that one. That's a very good question. And at what resolution it's being used? Because of course, one thing we did do, I forgot to mention, we produced a 1 kilometer and 5 kilometer product based on this, just by aggregating this and reducing the uncertainty. Because that was asked for. I know that. People said, my climate model can't run at 250 meters. That's too many grid cells. I can't do that. So we want a more general product. I mentioned Sobler had 1 degree, and that was to some degree useful. So, okay, sorry. Hey, don't have all the answers, but I know, let me really think about that. Thanks. Yeah.
You talk about this prediction uncertainty. Do you see cases or reasons when some cases on certain level is so high, you might leave it blank, like no information? But in last,
Yes.
you quoted saying,
Should we leave a blank in the map, you mean?
yeah.
Yes. And there are two ways we're handling that right now. And I mentioned one is what we call the area of applicability. That's actually not so much based on the uncertainty as such, but on whether the training points well represent an area we're going into. So a good example would be, let's say we don't have any points in the Sahara Desert or something like that. So we have nothing with such low rainfall and this temperature distribution. And you would say, in that case, you might say, we won't even predict in there because our multivariate space of training data of covariance, we don't know anything about that area, right? The other is this quad map idea that developed by Jose Pagarian, where you look at the uncertainty within the pixel and you keep expanding the pixel until the uncertainty goes down. Because as you keep expanding the pixel, then you keep averaging the uncertainty by the square root of the size. So you get to the size of the pixel that will have sufficiently low uncertainty according to your criteria. I guess if it got to a pixel that was too large, you'd say don't do it at all. But I really like that idea because you can say, at least in the pixel, I don't care how big it gets, the average and the standard deviation, I'm fairly confident in. Not at any point in there, but overall in this area. So that's the way. But yes, the concept of is to leave maybe some blanks in the map. But these land surface modelers they don't want blanks in the maps. People will want yeah, but it's a very good question. That's the concept. We're really acutely aware of this. It is all, serious visual saw mappers.
So I want to follow up on Michael's question, like in an opposite way. Are there exercises where you adjusted pixel size and uncertainty for specific applications to show what it would take?
I don't think that's good. I should look again to see we wouldn't do that at the producer level. And I should see if people have done that. That's been done for block kriging. It's been done, I think, because what you can do, again, what you do when you're increasing the pixel size, you're now only going to be making a recommendation for that area or only modeling based on that area where you'll miss differences within the area. And you're willing to do that. I mean, this is back to the before precision agriculture. When we sample the field, we go around the field and pick a bunch of cores. Actually, we're trying to represent the whole field, and we're going to treat the whole field the same. And then you can see the result of doing that by the crop growth and so forth. Now with precision agriculture and so forth, you can now see the finer scale. Yeah, that's a good, I should look to see.
Yeah, you make a really good point. And basically, that there's both socioeconomic decisions and real biophysical effects. Yeah, that's a good.
I think it comes down to what you're trying to get out of the soil. That's why I said, what are you doing with the soil map? And how accurate does it have to be for what you're doing? If a farmer is looking for management zones within a field, then the farmer is able to manage it so precisely, then that's the need, right? But if you're looking for more general land use planning, and you're looking for large areas, large areas that you will zone a certain way, you don't need all the detail. So, but I'd like to come back to yeah. Good. I knew I'd take to a good place. Good question. I'll take them back to our group also. So when you get together, just with the mappers, they're all talking about mapping methods. And we are trying to emphasize the usability. So anyway.
Great. So for the interest of time, we're going to end it there today. But if you have more questions or want to have a meeting with him, he'll be in 2104 tomorrow morning. If you want to stop and chat with him. Let's thank Dr. Rossiter again.
Operates. There is land. Oh, my doctor. Sorry, I went.